Okay, so our topic for this week is sensible and latent heat. Now, heat is a colloquialism, and what we really should speak of is not in terms of heat, but in terms of thermal energy. That's the more precise terminology. What is thermal energy? Thermal energy is the energy of molecular motion. So if you take, like, a book and put it on your desk, then it's at rest, so it has no kinetic energy. But if you could look with atomic eyes, you would see that all the atoms and molecules inside the book are zipping around quite quickly. So there's a fair amount of kinetic energy there. There's also some potential energy as these atoms and molecules both attract and repel each other a little bit. So the sum of all that energy is known as the thermal energy, or more colloquially as the heat. Now, thermal energy can be transferred between objects. In an isolated system, it will always go from the hotter object to the colder object. Um, if the system's not isolated, and say we look at a refrigerator that's plugged into the wall, then of course we can remove thermal energy from the colder object, say your milk in the fridge, and we can exhaust it to the warmer environment, which is the warm room. Now, in either case, the flow of thermal energy will lead to a temperature change, and we use the term sensible heat. And the temperature change is proportional to, and here's a symbol for proportionality. It's a Greek letter alpha. It means proportional or varies directly with. The temperature change is proportional to the amount of thermal energy transfer, or the amount of sensible heat. Now, there's another quantity that affects the amount of temperature change, and that is the object itself, what it's made of. And that quantity is known as the specific heat capacity. So the units of this quantity tell us, for that material, say water, aluminum, etc., how many joules does it take to warm a kilogram of the material up by a degree centigrade. So you see, for water, that number is 4,186 joules to warm a kilogram by a degree centigrade. But aluminum only requires 890, and iron and steel only require around 450. So if we put all that together, then we find that the amount of sensible heat, or thermal energy transfer, equals the amount of object you've got, the temperature change it undergoes, and then here is the specific heat capacity of the material, and that depends on the material. And typically those values will be given for you. So this is in joules, this is in kilograms, this is in joules to warm a kilogram by a degree centigrade, and this is in degrees centigrade, or it can also be in kelvins, because one step on the centigrade scale is equal to one step on the Kelvin scale. The degrees have the same size, the same magnitude. Okay, so this is the specific heat relationship. The sensible heat relationship. Q is sensible heat. It's a transfer of thermal energy that results in a temperature change. An example here, a dishwasher warming up some hot water, and it's warming it up from 6 to 60 degrees. So how much sensible heat is required to heat the 50 liters of water? Well, the amount of sensible heat depends on the mass, the material, and the temperature change. So we're told that 50 liters of water has a mass of 50 kilograms. On the previous page, we gave the specific heat capacity of water, 4186 joules to warm a kilogram up by a degree centigrade. And then we're going here from 6 to 60. That's a temperature change of 54 C, or 54 Kelvin. So units, kilograms cancel, degrees centigrade cancel, and clearly this ends up in units of joules, which is good because it's a sensible heat. Let me pause for that calculation. Okay, so there you see it. It looks like 11.3 megajoules. So that's the amount of thermal energy that would be needed to heat that water up in your hot water tank. Now, if your hot water tank is 90% efficient, how much electricity was used? Well, the efficiency ratio, recall, is output, useful output, over the cost. Now, the output in this case is the thermal energy of the hot water. The input is the electrical energy that was consumed, that was fed through the heating element on your hot water tank. Now we want to find the electrical energy, so we cross multiply this up and then efficiency down. And so we see it's the 11.3 megajoules of thermal energy we need to create. And we're going to use slightly more electrical energy than that. And that is 12.558 or 12.56 megajoules. Now, it would be customary to express that in kilowatt hours, I suppose. We could do that. We could say 12.56 megajoules. So to convert that from joules to kilowatt hours, we know a kilowatt hour is 2.6 million joules. So we divide, multiply through here, megajoules cancels, and we end up with 3.49 kilowatt hours, about 3.5 kilowatt hours. Okay, so that's an example of sensible heat. Now, there are times when thermal energy will be transferred between objects and there will be no temperature change. That'll happen when there's a change in phase. So if we have a block of ice and if the ice absorbs thermal energy from the room, if the ice starts off at zero, then it will start to melt. But during that melting, the temperature will remain at a constant 0 degrees C. If you keep on adding thermal energy to the water, eventually you'll reach the point where it'll start to boil. And at standard temperature and pressure, 100 C or 373 Kelvin, that'll stay at 100. And the temperature will remain at 100 until all of the water has been evaporated, has been vaporized into steam. So during a phase change, a temperature remains constant. There's no change in temperature. And the amount of thermal energy transfer then does not depend on the temperature. Instead, it depends on the amount of matter, the amount of stuff, and a constant which reflects both the material and the phase change that's taking place. So for water, we've got one latent heat for fusion, which is the transition from a liquid to a solid. That's fusion. That same constant will apply to freezing. We then have another constant for vaporization, and that same constant would apply to condensation. So when we are experiencing a change in phase, there'll be no temperature change, and the amount of thermal energy transfer, which is known as the latent heat now. So latent heat is a phase change. Okay, so imagine we start off with a block of ice at -5 C, and we want to warm it up to steam at 120. Well, the first thing we'd have to do is we would have to raise the ice up to 0. Now, that's going to be a sensible heat, and the amount of energy required to do that is mc delta T, but C, because we're dealing with ice, will be the specific heat of ice, which is actually different than the specific heat of water. It is, just give me a second to remember it. Okay, so here we are again. Yeah, so that's 2090 for ice, joules to our kilogram by a degree, and we're warming it up by 5 degrees C. So that's how you'd find that amount of thermal energy. At 0, that what was originally a block of ice is going to start to melt. And it will melt, and the temperature will remain constant. That is a latent heat. And that just depends on the mass, and then on the material, which is water, and on the phase change that's taking place. Because that's fusion, there's 10 kilograms of ice, and it's 334,000 joules to melt a kilogram of ice. Okay, so we've got to get to steam at 120, so we keep transferring thermal energy, then we end up with water at 100. That is again going to be a sensible heat, which we calculate using mc delta T. Now we're dealing with water, and so the sensible heat will be 4186, and the temperature change is 100 because we're going from 0 to 100. Okay, at 100 we will start to boil and produce steam. That's a latent heat. And the amount of latent heat just depends on the mass, on the material, and then on the phase change that's taking place. It's being vaporized. It's water. It takes 2,256,000 joules to vaporize a kilogram of water. Lastly, we'll warm the heat up to what is. Okay, so this will be sensible heat as we warm the steam up from 100 to 120. And sensible heat we calculate by mc delta T. Now this is the specific heat of steam, which will be different from water and from ice. It takes 1520 joules to warm a kilogram of steam up by a degree centigrade, and we're warming it up by 20 degrees C. Okay, so here's another example, a little bit more practical, a little bit more related to our course material. Aluminum. It takes about 200 megajoules to produce a kilogram of aluminum. That includes the mining and the smelting. This is what we call the embedded or embodied energy. However, the recycling process, so to make a new aluminum can, it would take a ratio of 200 megajoules to make a kilogram of that aluminum. To recycle the aluminum, though, we simply have to ship it and then melt it. So let's see how much energy that would take. Okay, so we're going to take a block of aluminum from, say, room temperature, 20 degrees C, and then we're going to warm it up to its melting point of 2,000 degrees C, and then we're going to melt the aluminum. And at that point, we'll purify it and then recast it and use it again. So let's see how much energy this would take. So first of all, we've got a sensible heat there of mc delta T, and then we've got a latent heat of ml, latent heat of fusion. So let's just work with a 1 kilogram block of aluminum. The specific heat capacity for aluminum is given as 890. So it takes 890 joules to warm a kilogram of aluminum up by a degree centigrade, and then clearly we're warming it up by about 1980 degrees C. Then we'll take that same 1 kilogram of aluminum, and it takes 398 kilojoules, or 398,000 joules, to melt that aluminum. So if you add that all up, you find that to recycle the aluminum and recast it, it only takes about 2.16 megajoules. Now, there are other contributions to that. You've got to truck it, etc., etc. And this number is actually a bit of an underestimate. It's a little bit greater than 2. It's actually about 8 in total. But you could see that it's a lot less than the 200, that's for sure. So never throw out aluminum, because we can recycle it and get recycled aluminum the quality is just as good as virgin aluminum, and so we can replace, or rather reduce the amount of virgin aluminum that needs to be produced just by recycling. Now here's our final example. Let's look at hot water use, and we have seen that our household energy budget is about 600 gigajoules annually, and about 4.3 gigajoules of that went for lighting. Now, let's try and justify the 18.8 gigajoules that are used for heating water. Let's imagine that the average household uses 200 kilograms of hot water per day. And let us find the amount of energy, first the thermal energy that's required to heat up that water. So it would be 200 times 4186, and the water we're going to assume is heated from 5 to 60. That's a temperature change of 55. Then next, the efficiency will be, as in our previous example, the output thermal energy over the input electrical energy. So we'll work out the electrical energy. and then let's see how much is it used on a per year basis. So this will be per day because it's 200 kilograms per day. So let's work out that calculation. Okay, so the energy per day. Okay, so we see that's about 46 megajoules per day of thermal energy. Then we divide by 0.9, and we see that's about now 51.6 51.2 rather, 51.16 megajoules per day of electrical energy. So now let's see what that is over the course of the year. And there you have about 18.7. We multiplied by 365 days in the year. There's 18.7 gigajoules of energy used to heat hot water. Now, a gigajoule is a 32-watt light bulb on all the time. So that means that the energy that we use to heat water in our households can be visualized as 18.7 light bulbs on all the. Sorry about that. 18.7 light bulbs on all the time. Or the more precise figure, 18.8. That's the national average. All right, so that's a look at sensible and latent heat and its application to a couple of problems of interest in environmental physics.